So string theory is a theory under construction that went through different phases where different things were discovered. And it's a theory of quantum gravity. So it's the theory of a quantum mechanics of space-time. So it's that picture of space-time that we have according to Einstein, where it's classical and definite. We replace it by a picture where we have a probabilistic distribution of different space-time shapes. And it's a theory that reduces to Einstein theory under ordinary circumstances. So ordinary circumstances, I mean the ones we experience in our everyday life or we experience throughout the cosmic history of the most of the cosmic history of the universe, where we are looking at things at long distances. And I'm not going to describe all aspects of this theory. We're only going to discuss one aspect, which is that it can describe in a complete way certain simple universes with negative curvature. So with the methods of string theory, we understood how to describe some certain, let's say, toy universes and simple universes in a complete way. So these are universes that have constant negative curvature, and we can describe the interior of these spacetimes in terms of a theory on the boundary. So these universes roughly have the shape of so-called hyperbolic space. Now this is a little map of hyperbolic space. So it's a space with constant negative curvature. And so when we project it to the screen, it gets a bit deformed. It's similar to when you take the surface of the Earth and you project it on a plane. Some regions get blown up and so on. Here, the opposite thing happens. Some regions get compressed when we put it here. And so here, all these fish have the same proper size, the same size in hyperbolic space. But when we project them to the screen, they get deformed. So the boundary here is infinitely far away. You have an infinite number of fish to get here. And also the size of these circles is increasing as you go out in rapid way. So the idea is that we can have a space-time that looks like this, and we can have particles that live on a surface that has the shape of this boundary. And so roughly the idea is that you can have the interior, and you can have, let's say, a particle moving in the interior, and that particle moving in the interior is represented by strongly interacting particles that move on the boundary. The interesting thing is that the particles on the boundary do not feel the force of gravity. I mean, they just live on a fixed space-time. There is no gravity, and so it's a conventional quantum theory that lives on the boundary, so a conventional interacting system. But it's strongly interacting. So I try to represent the strong interactions through this complicated motion. It's one way to represent it, but and in this way, we can describe particles that move in the interior, but we can also describe even black holes that are in the interior. So if we have a big black hole here, it will be represented by a fluid of very strongly interacting particles. This should really look like a more continuous fluid. I hear a rant of patients drawing all these particles. And so it should be a dense fluid of strongly interacting particles, and which can be many different microstates. I mean, you even rise to the black hole entropy. So the temperature and entropy of the black hole is related to the temperature and entropy of these particles that live on the boundary. So in this picture, the microscopic constituents of the space-time are these things that live on the boundary theory. So it's a somewhat in this picture they are not associated to the location here of the black hole, but we have a precise description of these black hole states only by going here far away and finding these particles. So the important point is that the theory of the boundary obeys the rules of quantum mechanics, and if you accept this relationship, then so does the black hole in the interior. And so then black holes end up being consistent with quantum mechanics. So I'll now try to, well, this is a little strange because you are describing a higher dimensional space, which is this interior region, in terms of some things that live only on the boundary. And for that reason, this notion has been called that of an emergent geometry. So you have a system which is fundamentally defined here on this surface, and out of it there is some effective description that involves one extra dimension. And just to explain roughly how we think this works, we'll just do a kind of analogy. So it will be a verbal analogy without any formulas. So let's imagine we have a sentence, okay? Here is a random sentence so one can write down. So for example, the sentence reads, if a man does not keep pace with his companions, perhaps it is because he hears a different drummer. Okay? So it's some sentence. Now, when you have a sentence like this, you can analyze it, right? Like you do in school of syntactic analysis of the sentence. So you can, in your mind, you did that. You analyze this sentence. You hear the various words and sounds, and you recognize the different words. You group the sounds together to form the different words. In your mind, you also group different sets of words to form partial phrases. Okay, I guess in grammar they have different names. I don't remember them now. You have various clauses, right? And there are also some distant correlations between the words. So, for example, here the word man is correlated with he and also his, and this notion of keeping pace is correlated also with the notion of a drummer. Okay, so we have all these correlations, and in your mind you analyzed this sentence already, and you found all these correlations and features in order to understand the meaning of the sentence. Now, the idea is that when we have the state of a system that lives on the boundary, it's a bit like a sentence like this. So it's a very long and complicated sentence. And what the bulk spacetime is doing is characterizing, is sort of analyzing this sentence and finding patterns in this sentence or patterns in the state of the system at the boundary, summarizing the patterns of correlations that we have in the system. And then we might have these long-distance correlations might correspond to particles that are moving in this fixed space-time. Okay? Now, this space is somehow curved because there are more somehow short-distance correlations than longer-distance correlations. So that's one reason why we have this space with negative curvature. Now, what would correspond to a black hole in space-time? So let's go back to this sentence that we had before, and let's say we change some words. So for example, instead of his, we have its, instead of he, we have she, and instead of drummer, we have lecture. So we've changed a few words. And because we changed those few words, we lost some of the long-distance correlations, right? Now the correlations between man and he, his, and she, they are lost, right? They are not correlated, and again, the same happens with the other case. But shorter distance correlations still are present, and the sentence is grammatically correct, okay? Except if you have that these long distance correlations are not holding, the clauses are still there, and so on. So in this case, we lost these longer distance correlations, and in this picture, we would say that there is a kind of black hole horizon here. So a sentence doesn't make sense beyond a certain level. So it makes sense up to at short distances, or at the level of a few words, but when you take it as a whole, these long-distance correlations are lost. We have a kind of horizon. We can change a little more. We can change a little more in the sentence, and if we change a little more, then it's as if the horizon grows bigger, and it's closer to the level of words, and in the end of the day, you can change all the letters, and then we would say the horizon is all the way up near the boundary. So the black hole grows as you start changing the sentence, and the area of the black hole is, roughly speaking, the ignorance you have. It's how much you've changed. And the area growth, this notion that the area grows is related to the idea that if you take a sentence and you start editing the sentence randomly, you are likely to mess up the sentence than to make a reasonable sentence. Okay. Now, let's imagine that we started with a sentence, and this particular sentence here was produced by a reversible process. So we took the original sentence and we applied some transformation. These type of transformations are called encryption processes, where we take a sentence and then we change all the letters in some deterministic way, but we get something that looks completely random. So if you don't know how you change the letters, then you would say, okay, I have a black hole here, right? So these encryption processes are what normally is used to send your credit card through the internet and so on. So it's a familiar concept. But if you don't know, so for the thief that is trying to figure out what your credit card number is, you would just see this as a black hole. Now, if we know what the process is, and then we can invert that process and recover the original sentence, right? So if the thief knows how it was encrypted, then he would be able to recover the original sentence. So the idea is that the loss of physics on the boundary, so on the boundary we have this state, so that's the state at some particular time. But then as time goes on, we have the loss of physics act by changing these letters, but they change the letters in a way that might look random if you don't know what the laws of physics are, but it's an algorithm that is determined, and we know what it is, and for that reason it's also reversible. And so for that reason, we think on the boundary we can reverse the formation of this black hole, so we can take this string of meaningless symbols and reverse that encryption process and go back to the original meaning of the sentence. So that's what it would mean to get the information out of a black hole. This is what we mean by. So if you don't know this encryption process, you think that you lost the information, but once you know this loss of physics, you can recover the original information.